It's the largest milling machine in the world. It can handle 500 tons of steel at a time, perfect for the kind of project they're focused on here at IMSA.
Right now, here in IMSA, we are building the largest Kaplan turbine ever built, 230 megawatts.
Kaplan turbines are located at the exit of a dam and are used to create hydroelectric power, and they are huge. With a generator on the top and ship-like turbine blades on the bottom, the shaft alone is higher than a 3-story building.
The weight of the complete shaft is 145 tons, and it has 13.5 meters length.
And IMSA is building 10 of them.
The units are very big, so the price is the order of $70 million to $8 million each unit.
It's the largest hydroelectric project ever attempted anywhere, and Juan de Miguel is the man in charge.
Until the time we deliver the first unit, it will take like 5 years. After the 5th unit, we will be delivering every 2 months 1 unit, so it's almost 2 more years.
It all begins with the turbine blade. They're very similar to a ship propeller.
We are building now 10 machines, each one of them with 5 blades on the runner. This is only one blade. This weighs around 16 to 17 tons.
The surfaces of the blades are rough for a reason. The ridges make them more hydrodynamic and more efficient. But long before the blades and all the other components are constructed, everything is scaled down. At $80 million a pop, you want to make sure all the parts work, but more importantly, you have to prove to your client that you'll be able to deliver the power you promised.
You have to have a physical model, a small-scale model, to test in a hydraulic machine laboratory to check the results.
Every component that goes into making the Kaplan system gets its start here in the lab at 1/24th scale.
What you are seeing is the actual water income in a dam. As you can see here, this is close to 1.2 meters high. Once we scale up, it means the water intake will be close to 30 meters. We're talking about 700,000 liters per second.
All the models here are developed in our center with our own technology. We measure the efficiency of the model, and then we could scale up the efficiency for the prototype.
Tightness is important for us because whatever we have as a gap between the blades and the fixed part, it will be a place where the water can through without moving the blades, which is what generates the energy.
On this model, the gap between the blades and the housing is 0.2 millimeters. That's half the thickness of one of your hairs. This is the blade housing at 1/24th scale. And this is the full-sized version. And that brings us back to the milling machine. The tools will take off just enough metal to provide 5 millimeters of clearance for the blades.
We're talking of a piece nearly to 200 tons, 9 meters in the internal diameter is probably 9.5 meters on the outside.
The machine turns at 12 revolutions per minute. Any faster and you run the risk of the tools overheating. It's all hands on deck at the Mendoza plant as 1,400 employees work 3 shifts, 24 hours a day to get the turbines finished. They've been hard at work for years, and they have 3 more years before all 10 turbines have to be delivered to their client in Venezuela.